So number 14, it's asking to find the formula given by the sequence, and then it goes ahead and gives us the first 5 terms and saying, okay, if this pattern continues on, how would you express that in a closed form? So to do this, we're trying to find some function of n such that for each n value, it corresponds to each of these. So it has to satisfy that. And to do this, we really just try to find the pattern and then model it using a function. And there's a lot of common ones that pop up a lot in these problems. So a little toolbox here before we even get into this one, and then maybe one of these will apply, or maybe multiple. Even numbers, odd numbers, those things pop up a lot. So to represent them, you just use these two things. Geometric pop up a lot as well. So you have some ratio between each of the terms, starting at the first term being a sub 1. An arithmetic sequence, so you're adding or subtracting the same thing from every single term, starting at a sub 1. That's another one that pops up a lot. And then also alternating. So if every other term is positive and every other term is negative, then something like this might be occurring, or maybe something like this, depending on if you start off positive or you start off negative. And then finally, just looking out for perfect squares and cubes and things like that. So using all these pieces, generally we can find something that defines the sequence, as long as it's not recursive or something like that. So in this case, let's look at our numbers. So ignoring the sign, usually like right away we see this as alternating signs. So let's just alternating signs. So that's one component, and we're going to piece together the pieces. The other component is that it seems to be dividing by 4 every single term, ignoring the sign change. So what that means is that there's a common ratio of 1/4, and we start at 4. That's our first term. So if we were to put that into the geometric formula here, geometric sequence, we'd have 4 as our first term, as a sub 1, and then 1/4 to the n minus 1. And just check that. If we plug in 1, assuming the sequence starts at 1, if we plug in 1, we get an exponent of 0 on the 1/4, so we're just left with 4. That's exactly what we want. If we plug in 2, 4 times 1/4 is 1. That's exactly what we want, again ignoring the sign for now. So this is definitely a key component of our formula. Now, just to take into account the sign changing, we want to throw in either, where did I write it, this or this. In this case, we want to use the second one because the first term is positive. So here, n plus 1 for the 1/4 n minus 1 would work just fine. And that's because we're starting at 1. So 1 plus 1 is an even exponent. So for odd indices, this would be positive, and that's exactly what we want. We want it to be positive at 1, 3, 5. So at odd indices, it's positive, so we'd use n plus 1. If it were flipped and the negative 4 here was negative and this was positive, and that continued on, we just use n in the exponent. So this is our function that describes the sequence. And there you have it.